we are now recording. So let's get the slideshow set up for the current slide. All right. Now, before we get going on this, let me make a couple of other announcements. Well, there we go. Okay. Hopefully that's coming on now. Number one, finally, it was either before, it was sometime over the weekend. I got some of it done on Friday, and the last of it finished up over the weekend, I think. That I got your syllabus completely updated, the research paper instructions completely updated, my locator card for the first mini-term completely updated, and I found, in previous classes, here's my sweating Richard Cribbs, okay. Good. I see now why Nicole is sitting on that side of the room. Okay, I don't blame you at all.
I understand, yes. I gotta go get some more.
Okay. All right. Okay. So I found from previous terms either websites or YouTube videos or other things that either I found might be useful to you or the other students had told me they found useful. So I loaded those on Blackboard under content. Everything is under content. Syllabus, research paper, locator card, and these other YouTube videos or websites. The thing I did not get loaded on because I didn't have my CD or DVD over there, I could not load the PowerPoints. I'm going to try to do that. I hope I can get it done this afternoon. That's one of my things on my to-do list, but as I was checking emails both Friday and over the weekend, I just kept getting more and more things that I need to do this afternoon. So whether I have a chance to get them all done this afternoon, I don't know, but I hope to get this done, the PowerPoints out there. Okay, also, I got your YouTube video set up. I already had it set up, but I got the playlist address, and it's out there. So what you'll find now under content is syllabus, research paper instructions, locator card, a number, I can't remember how many, of websites or YouTube videos that other students, or either I found or other students have found. They said they found them useful, okay? And I've got the link to the playlist for the two videos we've had so far in this class. And that is entitled Math 125 YouTube videos, okay? That's the one from this class. The others, there's one I think called Math Vids or something like that. I don't remember if that's for this class or not, but visual calculus, there's several that either other students have found or I found that I thought might be useful to you. So you can go link on those. But I don't have your PowerPoints out there yet. I hope to have those done today. All right. Any questions for anything we've done up till now? All right. Now, Section 2.2, we did Section 2.1, which sort of was an introduction to what we mean by limits. Rates of change, tangent lines, that concept. Now we're going to do in 2.2, continuing in limits, and we're going to look at both the numerical and graphical approaches to limits, okay? Which is basically what we're doing before. We're doing graphics, but they're just continuing this. But we're going to start it with a really bizarre function, okay? The goal, and both of you have your text, right? Yeah, okay, I won't read it all. But how do the values of a function f behave when x approaches a number c, whether or not f of c is defined? That's the question. And they're going to start with this function right here. I think I'll go on and blow this up because I was going not to because I thought I'd need to write something first, but I'll go on and blow this up and I'll just talk off of this one. can't write on it once it's blown up. I can't talk on it. Here's the function we're interested in. Sine x over x. Okay, when you look at that function, what's one of the first things that comes to mind?
It can't be 0 in the denominator?
Aha, very good. It looks like this is not defined at 0. And it's not. You cannot ever divide by 0, ever. But I think I mentioned to you before a distinction, and I don't think the book makes a big deal about it, but when I learned calculus, I found it was helpful, okay? Because they did make a bigger deal about it. When x is approaching 0, that means you can't have 0 in the denominator, right? Okay. But take a look at the numerator. What happens to the numerator when x approaches 0? Oh, that's cosine.
0. So it becomes 0.
It becomes 0 as well. Now you have a form that's 0 over 0, which is not undefined anymore. It's now indeterminate. So we don't know. If this were a cosine x over x, completely undefined, don't go any further. That's 1 over 0. It can never happen. But 0 over 0 may have a limit. It may not, or it may. So that's what we want to investigate. Now they're going to investigate it two ways, as the section title said, numerically and graphically. So what they're going to do numerically is try to get close to 0 from the left-hand side, or the right-hand side, from the positive side. Well, they're going to start with 1. And by the way, when you see sine of x, what do you know x is in? What would x be measured in?
Degrees.
No.
Excuse me.
Radians. Anytime in calculus, always assume radians, because all of your things work best in radians in calculus, okay? So, actually 0 radians is 0 degrees, so it's not going to make a big difference, but let's use radians. If we were to plug in a 1 here and a 1 here, sine of 1, now be sure you're in radian mode, that's going to be some number, and it happens to be 0.8, blah, 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 okay? Okay. Now, get closer to 0, like 0.5. Put sine of 0.5, be sure you're in radian mode, over 0.5, and you get this number. Get even closer to 0, 0.1, and you get this number. Okay? 0.05, you get that one. 0.01, you get that one. 0.005, 0.001. You can keep on trucking, and soon you're just going to have, I'm not going to say how soon, but in a bit you might wind up with 0.999999, or you might wind up with something different. You might start getting some other digits here. You got up to 0.999 and then kept putting in smaller and smaller numbers, and you start getting other digits showing back up here. Don't stop, because you've already exceeded the limits that your calculator can do. Okay? Because your calculator is trying to calculate something in a precision far beyond its capability.
That's pretty good. That's what, 10 places right there?
This is 1, 2, 3, 4, 5, 6, 9, 7, 8, 9. 9 places.
That's incredible.
Yeah. And just at 0.001. Okay.
Okay, my sign for 0.5 is actually showing 4.7.
Okay, now do this again. Say it again.
My sign is sign 0.05.
Did you do it?
0.05, and then divide it by 0.05. Sine of 0.05 divided by 0.05.
Okay.
You get the same thing now? Yeah. Okay. Now, does it give you does it look like you're heading somewhere? Getting closer and closer to 1, but not quite getting there, okay? As x is approaching 0 from the right-hand side. Well, let's go over to the left-hand side, okay? Negative x's. And sine of -1 over -1 amazingly gives you the same value, okay? Now, it's not too amazing if you think of it this way. Sine is an odd function, which means that would be the opposite sign SIGN sign. But x is also an odd function, so you odd over odd basically acts even, and sure enough, it is acts even. Okay. 0.05 gives you exactly the same value, negative 0.05, because this is negative and that's negative. 0.01 gives you the same value as this one does, because both are negative. 0.05, just down the line they are. So sure enough, as x approaches 0 from the positive side, that's what the plus over here means. Now sometimes you'll see that superscripted. That I think I like that a little bit better, but that's fine. You know what they're talking about. F of x is approaching 1. As x approaches 0 from the negative side, it's also f of x is approaching 1. So that gives you a good idea that f of x, the limit of f of x, and f of x is this ratio, is 1, even though it's not defined at x equals 0. You still can't define it there, but the limit is 1. And this is Samaria, right? All right. Just missing Rodney, and we'll have perfect attendance. Okay. All right. Now, I hope I'll have to check on this. I don't know. For the three of you, really good shape. Everything's fine. But if you have any friends, I think I announced this last week, who had not paid, they may find themselves removed from class this week, okay? Because they did that, I think, actually last Tuesday, didn't they? At the end of the day on Tuesday. Now, they couldn't put anyone back in, even if they got paid, until sometime over the weekend, because they were doing Pell Grants and they couldn't do anything to it. So hopefully if people paid since then, they've gotten back in the class. But it really makes for a difficult thing, because you're removed from Blackboard, you're removed from Student Suite, and that also meant you're removed from Faculty Suite. So if I had put your attendance in to begin with, then it was taken out, and then I have to go back and put it in again. So if you see that you're not, y'all are all there because you were paid. But if you have friends who say, "Hey, I don't show any attendance here," well, that's because they wiped you out, and then they may have put you back if you completed payment. It's somewhat of a strange way to do things, what they did. So anyway, numerically, you see what's happening. Okay? Now, graphically, here's what's happening. If you were to plot those points we just had and go beyond those, okay, notice there we started at plus 1. This is pi, which is 3. So plus 1 would be about here and minus 1 about here. So we were dealing everything in that little range there. And sure enough, the closer you get to 0, the closer you get to 1. But at 0, there's a hole in the function, because you can't ever divide by 0. The graph is f of x is equal to sin x over x. You can't ever divide by 0. Even though it has a limit, both from the left, right, and from the left of 1, it's still not defined at 1. Okay? And if you were to go further out and have, say, at negative pi and pi, okay, sine of pi is 0. But you're dividing now not by 0, you're dividing by pi. So this is going to be 0. And notice here, you go down, up, and basically if you went on out there, that limit as x goes to infinity is 0, and this one gets closer and closer to x-axis. That's also 0 as x going to negative infinity. At x equals 0, they're not defined. But the limit is 1. Okay? So numerically and graphically, you see that's what the limit is. Now, we also say f of x approaches 1 as x approaches 0. You can't say it's equal to 1, but it approaches 1 as x is approaching 0. Because x can't be 0, because that would have a 0 in your denominator. But here's sort of a conceptual insight. They don't show the conceptual insight. Sorry, okay? I'll try to show it, okay? Boo hiss, okay. Let's break this. I already sort of hinted at it. into the two pieces. I don't know why my pen went back to red. Oh, I never have changed it. I can't do black, so I'll do dark purple. Okay. If I were to graph, let's call this g of x is equal to sine x, and h of x is equal to x, right? Then f of x is going to be g of x divided by h of x, right? Okay. Well, let's do g of x. In fact, I probably should do different colors here. Sine x, basically it's 0 here. Yeah. 1 at pi halves, and 0 back here at pi. Negative 1. This is pretty ugly, isn't it? At negative pi halves, 0 here, 1 at there, 0 here, and so on. And over here, sine is negative 1 at negative pi halves, 0 here, plus 1 here, 0, negative 1 here, 0, and so on. So here's your sine function. Probably not the prettiest sine function you've ever seen, but it's a sine function. Now, I do want to point this out to you. This scale sort of stinks because this much is more than 3 and that much is 1. So they've got the y really extended and the x compressed. So that means your y is equal to x is going to be going like this rather than 45 degrees because they don't have an equal function size. Yes, I should have. Let's back off of this. In fact, no, I'm not going to do that.
Correct me if I'm wrong, but it almost kind of looks like a cosine function. Isn't that kind of how it...
That's how the cosine function looks near 0. You're absolutely right. But it crosses at minus pi halves and pi halves.
Exactly.
So or fast enough. Yeah, exactly. But yeah, it does act like that. Let me go on and do it on... I'm going to clear this because I was being lazy. Let's do another graph here. Try to space as best I can. All right. Let's do one. Let's spread it on out some. Okay, let's do it here. Let's call this one. No, that's not going to work. Let's do this as 1, and that's 1. 2, 3, 4, 5, 6, 7, 8, 9. We don't need that many. Minus 1, minus 2, minus 3, minus 4. 1, minus 1. We don't need these up here, but we'll put them in. Okay. All right. Because the sine function is 0 at 0, so let's do it now. What do I call it? G of x is equal to sine x. Okay? So it would be at 0, 0. Now, the next place we know is pi halves. Well, if this is 1, 2, pi halves is just a little bit more than 1.5, right? Because pi is 3.14, pi halves would be 1.57, okay, approximately. So it's 1 here, okay, and this is 3. Pi would be here, so it's 0 here. And then, a little past 5, it's going to be minus 1 here. By the way, that's representing, whoops, put it in the wrong place. Okay. I wish they had, it's at minus 1 here. I had it too far over. Okay. Over here, it's going to be, here is a minus 1, here is a 0, and so on. So your sine function goes between, yeah, something like that. not a very pretty sign function, right? Okay. Let's do h of x. You pick me a different color. What color you want h of x to be? Green. Dark or light? Let's do dark. It will show up better. Okay. H of x is going to be x. That's your denominator here. Well, that function, I can do that one. 1, 1, 2, 2, 3, 3, 4, 4, 5, 5. Yeah, that's your diagonal line here, right? Now, if I had drawn that first one halfway decently, which I didn't, what you find out is these two functions basically lie almost on top of each other near zero, right? The slope of this one's obviously 1, and I'll tell you the slope of this is also 1. So therefore, they lie on top of each other almost always. So the ratio of those two is going to be 1, and that's what this is. Your f of x is the ratio of g of x, h of x, sine of x, x. So no wonder its value is 1, or in the limit is 1. You can't actually divide by 0, but the two functions are the same value there as you get close. And then after a while, the numerator, actually, I haven't drawn it well, falls off faster than the denominator, okay? The green line should be above the curved line here. I got it closer down here, it's not right. Because the curved line curves away from it, the green line, they have the same slope here, but this is moving downward, that's moving, yeah, like that. So this is decreasing after that. It's going to be 0 at this place. Yeah, this place and this place. And sure enough, that's what these two represent right here. And then again out here, and that's what these two represent. And then again, so. But notice this keeps climbing. And every time they're both positive, of course that's going to be positive. But when this goes negative, this one's positive, so this goes negative. But it only is negative in between those two. This is 1 pi and 2 pi, approximately, okay? And that's when it's negative, then they're both positive again, but they're getting smaller because this is a smaller number than that. That's in your denominator, so the fraction's getting smaller. Same thing here, they're both negative here, so negative over negative is positive. And the values are the same. So that's going to be close to 1, getting closer and closer to 1, but falling away, but still positive because they're both positive up to here, and then this goes negative then, because this is positive, that's negative. So again, that's what's happening down here. So that's basically what's going on. The key here is the slopes are almost the same. The two functions line up on each other almost identically. That's why the limit as those two is going to be 1. Because you're dividing the same number by itself in this range here, almost by itself. The green line's just a little bit greater, so they fall off from 1, but the limit at 0 would be 1, because they do have the same slopes there. And those would be the same values. Okay. That's the graphical insight. Can you always count on that? Not really, but it usually is a good indicator. A good indicator that they're going to have a limit. All right. So now we're ready. What is the definition for a limit? Okay. So let's focus in on it. Now, assume that f of x is defined for all x's on an open interval containing the number c, but not necessarily at c itself. So f has to be defined everywhere on this open interval that contains c, except it may not actually be defined at c itself. Everywhere else it has to be defined. Then we say that the limit f of x, as x approaches that value c, approaches whatever that limit is, L. What is that limit? It approaches L if the difference between the f of x, evaluated anywhere near c, but not necessarily at c, minus L becomes arbitrarily small when x is any number sufficiently close to, but not equal to c. Okay? there's a lot of weasel words in here, okay? Arbitrarily small, what does that mean? Sufficiently close, what does that mean? Well, we'll get to that. But in this case, if those two things are met, those conditions are met, that the difference between the function and the limit is getting closer and closer together as x is getting closer and closer to c, then we say the limit as x approaches c of that function f of x is L. So the one we just did, the limit as x approaches 0 of sine x over x is going to be 1. Because the closer you get x to 0, we saw, got to 0.9, 0.999, 0.9999, 0.99999, so that it's getting closer and closer to 1. So that means that limit does exist. We also say that f approaches L or converges to L as x approaches. F approaches that as x approaches c, or as x is close to c. Okay. So we can say approaches to or converges to L, or we can say f of x is going to L as x is going to c. So all these different ways to write the concept of a limit. Now, this is not a rigorous definition because it has these sort of weasel words in here. Arbitrarily small, sufficiently close. Later we'll give a better indication of what those are standing for, but for our definition now, that's going to do fine. Okay? Now, by the way, if you are interested, maybe for your paper topic, there's a little blurb here. The concept of a limit was not fully clarified until the 19th century, way after Newton, way after Leibniz. You know, the French mathematician Augustin Louis Cauchy, I think is how you pronounce, Cauchy, who lived from 1789 to 1857. If I'm not mistaken, both Newton and Leibniz were already dead by 1789. I'm not sure on the dates, but I believe they were. Gave the following verbal definition. When the values successively attributed to the same variable approach the fixed value indefinitely in such a way that as to end up differing from it by as little as one could wish, that's arbitrarily close, okay, as one could wish, this last value is called the limit of all the others. So, for example, an irrational number is the limit of the various fractions which provide values that approximate it closer and closer and closer. Okay? Now, you know that the square root of 2 is an irrational number. It's 1.414 blah, 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 and they just keep on going, but it's getting closer and closer to the actual value. You just can't write enough digits to get you the actual value. So we write it square root of 2. So everything we do, your calculator is giving you the limit. When you do a calculation, it gives you the limit of that thing. If you did the square root of 2, that takes you to the nearest 9 digits or something like that, but it's still an approximation. It's not exact, okay? That's what a limit basically is. It's getting closer and closer to a value, but not actually getting there, okay? So we'll give better definition of arbitrarily small is sufficiently close shortly, okay? Not quite there yet, but Cauchy could be a legitimate paper topic. So could you, huh?
Just out of curiosity, how did limits really come about? I know you said that, Sir Isaac Newton really, developed calculus kind of, and, others from the ground up, but how did they just realize that, graphs needed to start getting more and more precise, and it just, that's how they found certain holes and stuff in graph, or how did it kind of come about?
Okay, did I tell y'all about Archimedes before?
I don't think so.
Okay. Archimedes, 200 BC. He was dealing with it. He didn't call him that. But here's what he did. When I go to write on this, of course, it's going to shrink, but we've already talked about this, so let's just, okay. Good old Archimedes. He was a brilliant mathematician, an incredible engineer, and he was just a man way ahead of his time. He was doing this kind of stuff. And he was also, of course, very inquisitive. Okay, a thinker par excellence. Okay, if you think about it, even back then, 200 BC, they knew the area of a square. I don't draw squares very well, right? Okay. What they couldn't figure out is what's the area of a circle. That's a lot harder to figure. But since he knew the area of a square, I just started with square. He could have started with equilateral triangle. He did a square on the, and these should be touching here and here and here. My picture obviously is not good. This is called a square, the largest square inscribed within a circle. You can give me the area of that square. You can also do the smallest square circumscribed by the circle. In other words, the smallest square outside the circle. They touch right on the ends. I don't have it drawn very well. Here, 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 and here. Okay? So he can do the area of those two squares, and he knows the area of that circle in between is in between those two. Right. Okay? Now, that was a pretty easy figure to do. They knew how to do regular pentagons too. I don't draw them very well. That's 5, isn't it? I think it is. And a circle around that, and then a pentagon that circumscribes that circle, you know. And that would be even closer. If I could draw it well, it would be even better. And then if you can imagine, you could, and by the way, do you know the area of a pentagon? Probably not. But see, he knew how to do it because you can break this into equal triangles, isosceles triangles. Right. 5 equal isosceles triangles and add those together. Now, this is before calculators or anything. He's doing all this by hand. Okay, the one inside, the one outside, and that's going to be even closer than that. And then you can imagine, go to a hexagon. I can do that a little bit better. Not very much. You know, like this, draw the circle around that, and then draw the hexagon outside the circle. And you can see they're going to get closer and closer and closer. Octagon gets even closer. Now, he had to do the formulas for all these inside and outside and figuring out what those lengths were. But he could do it. That was all math. It could be do. And this is way before calculus. And then just keep getting bigger and bigger, more and more sides, and you get closer and closer to a circle. I mean, octagon's pretty close. Dodectagon, and then that's a 12-sided figure, a 15-sided. Miserable to calculate, but you could do it. And he could do it inside and outside, and then take the average. And after a while, he called this method, by the way, he approximated the area of a circle to a really close approximation. Why did he stop? Well, what did he call this method? The method of exhaustion. Okay? Literally, that's what he called it. Because get as close as you need to, but at some point say, okay, I'm tired of doing it anymore. I'm going to take that as close enough, you know. Because it's always going to be between the two, and he could calculate those two precisely, and he got it come up. But he never could get exactly what the circle was. Well, in a sense, he was doing a limit then, too. Because he was getting closer and closer to the area of a circle. Could never really get to it using precise formulas that he had at his effect. Why could he not? What is the area of a circle? We know, don't we? What?
Area is 2 power? No,
that's the circumference.
It's
move the 2 over there.
Yeah. So
Power squared, exactly. Okay? Except I can measure that radius as precisely as I can, but pi is an irrational number. So I can't ever tell you exactly what the area of that circle is. Ever! Because it's an irrational number. Okay? So you can only give me a limit, an approximation to it. Okay?
So in the okay, so I get the in inscribing and
Right, circumscribed, right.
But how did he just plug in values for the like the square and the pentagon and stuff to have already?
Okay.
Do you see what I'm asking? Like
Right.
how I get the area and then right. But what about the values of the
Right. Okay, let's just say he took, let's do bigger than squares. Squares you could just do, well, no, even squares are going to be a little problematic. On this first one, if he knows the radius of the circle, he also knows the diagonal of the square. And he knows the diagonal of this square, okay? And if he knows the diagonal, I can't remember how much math he needed at the time. But even without this, here you have 4 isosceles triangles, and he could figure out what,
Then that answers my question. So he knew the circle.
He knew not the area, but he knew the radius of the circle.
Radius of the circle.
And that radius of the circle would then give him half of the length of the circumscribed circle. And then he did, and same thing here. See, this would give you that one, and where it touched here, that would give you that one. And it was just dealing with triangles then. And he knew one side of the triangle could calculate the other side.
I was working backwards. I was thinking that he knew the values of the objects, but didn't know the radius of the. But I got you.
Yeah, he started with the radius of the circle, and then he knew one length on the circumscribed and one length of the thing, and they weren't the same length. I mean, they were the same radii, but they were different parts of those things, and that's what he worked from. So, I mean, he was doing that. So we've always really done limits, This is a dumb example. But I can remember my father loved to argue. That was one of his favorite pastimes. And unfortunately, his number one son, my older brother, he loved to argue. And I remember one trip from Georgia to North Carolina, or vice versa, coming home. I think it was North Carolina to Georgia. Grandparents lived up there. That they started arguing about how far it was. And they were, by the time we got close to home, they were arguing about the difference of a quarter of a mile or something like that. And I was saying, they had argued the entire way home. The entire 5-hour trip, 5-hour plus trip. It was driving me nuts because I don't like to argue. And they were, by the time they were arguing over a few hundred feet or yards or something like that. What difference does it make, But they were both taking limits. They didn't know they were taking limits. My father may have known that, but my brother sure didn't know. But they were estimating the distance, which is, in a sense, a limit. Yeah, without actually doing, we do it all the time. How long is it going to take to get there? Oh, we've got another hour to go. Well, it's not going to be exactly an hour, but, as you get close, well, we'll probably be there in 43 minutes. We're always doing limits. We don't know exactly what that last number is, but we're estimating what the limit is going to be. I don't know if that's a good example or not.
It is.
I just made it up, so let's pretend it did. All right, let's look at example 1. They don't do example 1, so let's do example 1 here. Use the definition we just had, that was this one over here, to verify the following limits. What's the limit as x approaches 7 of the number 5? So in this, 5 is going to be my f of x. Okay? Now, if you were to graph that, f of x is equal to 5. How would you graph that? X equals 0, what's f of x? 5. Okay? When x is equal to 1, what's 5? What's f of x? 5. If it's negative 1, 5. This is, if it's 7, what is it? 5. It's always 5. It's a constant function 5. So that's pretty easy to do. The limit of 5 is x approaches 7, or as x approaches negative 7, as x approaches negative 7/3, or whatever, it's always going to be 5. By our previous definition, that the difference here becomes arbitrarily small when x is any number sufficiently close to 7 that 5 minus 5 is arbitrarily small. It's 0. Okay. Yes, you can't get any closer than that. So yeah, f of x approaches 7 as x approaches 5. Because f of x approaches 5 as x approaches 7. Because f of x is always 5. So that's a dead giveaway. It is 5. Okay? Now, what we just did was plug in x where x showed up in the function. Well, x doesn't show up in the function. The function is 5. So the limit of 5 as x approaches anything is 5. As x approaches 0 is 5. It's 5. All right, now here's another one. Here's the b part. What's the limit as x approaches 4 of 3x plus 1? Any guesses?
Would be like -1/3.
No, x is approaching 4. You're having x approach 0, I think. No, I don't know what you're doing. You're letting f approach 0, I think. But that's not what it's asking for.
Okay.
As x approaches 4, limit of 3x plus 1. Say again? You could graph it if you wanted to, and they did in the book. If y'all don't have your book, so let's graph it. Well, they didn't. They graphed something else. I don't know what they were graphing there, but if you did graph that, you would do what? Give me an x, huh? Yes, exactly. First thing to try, plug it in, just like the lake, right? Now, I sort of said that here. Plug in x equals 7 here. There is no x. This is 5. It's always going to be 5. But here, you're letting x approach 4. So plug it in and see what you get. And what do you get? 13. There you have it. Okay? Now, yeah, now here's where you worry. I don't know if this is what you're asking. Here's where you worry. If you had 3x over 1 over x, then you have problems. The numerator is approaching 13, but the no problem there either, as it's approaching 4. Not an issue. Yeah, not a problem. Just plug in what you have. But if you're letting x approach, or 3x plus 1 over x minus 4, problem. Your numerator approaches 13, but your denominator approaches 0. And 13 over 0 never can exist, ever. So that has no limit. Now, let's go to Trey's -1/3.
Sorry.
Okay, that he used there. So as x approaches -1/3, this is going to be -1 plus 1 is going to be approaching 0. And then you divide that by x minus 1/3, as this x is approaching 1/3, that's going to 0, and then you do x minus 1/3 down here, and now you'll have this indeterminate form because it's 0 over 0. Can't figure out what that one is. Now you do mathematical manipulation, graphing, or something else to see if you can find out if that has a limit or not. Okay. So first thing we try, plug it in, just like Blade. If you get a form that never gives you an answer, like 13 over 0, hang it up. It doesn't have a limit. If you give them something that's like 13, no problem there either. You know the limit. If you get something like 0 over 0, or the square root of, or the log of 0, or something else, or log of -3, you can't do any of those, or square root of -2 or something, then you might say the limit doesn't exist, or If you have something that gives you an indeterminate form, then you have to investigate and see what the limit is. What were you saying? I didn't quite. Yeah. If it is a number, you got it. Okay. Now, I want to do something else now, but I'm jumping ahead. So I'm going to resist temptation and we'll let it catch up with us. But no, I'm not. I'm going to go on and do it. Here's something else you could have done on this. That's the same as the limit of 3x as x approaches 4 plus the limit of 1 as x approaches 4. Now, we haven't gotten far enough to do this, but the limit of a sum is the sum of the limits. That's what we just did. And what's more, you could do this as the limit as x approaches 4 of 3 times the limit as x approaches, no, I put it in wrong. X approaches 4 of x, duh. Okay, sorry. Yeah, plus the limit as x approaches 4 of 1. You could have done that, and the limit as x approaches 4 of 3 is 3, just like the 5 was 5. Okay, that doesn't change. And the limit as x approaches 4 of 4 was x approaches 4, x is approaching 4. I mean, so this is 4. So 3 times 4 is 12, and the limit of 1, just like this was, that's 1. So yeah, but why not just plug it in there rather than mess with all the limits? These are limit laws that you can do those kinds of things. We haven't gotten there yet, but sure enough, it's true. Now, let me erase some of this anyway, enough that's going to be in our way, okay? And let me go on and blow up this. Boom. Okay, here we go. All right. Theorem 1. For any constants, K and C, K is the German word for constant, C is our American English word for constant. So, for any constants K and C, the limit as x approaches C, just like we had x approaches 5, of 7, it's going to be 7, because this is a constant function, x equals 7. Okay, it may have been this one, I don't know where it was, okay? And as x approaches C, that's always going to be that. But the limit as x approaches C of x, as x gets closer to C, x is getting closer to C, all right? So the limit, the function is going to C. So these two things, and then the limit laws, they're going to allow us to do any limits we want to. And then it'll be legal to plug it in, plug it in. So we're getting there. They didn't quite let us do it before, but let's do it. Okay? Now, as I mentioned before, to deal with the more complicated limits, and especially to provide mathematically rigorous proofs, a more precise version of the definition that we just had is needed. In other words, those weaselly phrases like arbitrary, small, and sufficiently close, you have to actually define them better. We'll get to that, but they don't get there till a while yet. So let's now graphical investigation using a graphing utility, that's a graphing calculator or a computer program that has that. And if some of you have been, I think in Miss Martin's class before, have you? Doesn't she put a graphing calculator out there on Blackboard? So if you've got that, if you don't have a graphing calculator, you can use that, graphing utility that's out there. I don't think I have one on mine. I should, but I just never have remembered to put one on in time. But you probably have had it somewhere.
A really good website to get it, is it's this website called Desmos Calculator, DESMOS. You can even just Google search Desmos, DESMOS, and it takes you to a calculator that gives you all the functions, and you just type in what your graph needs to be.
Right.
and it will automatically graph it. And
Okay.
I think you can put in up to like 4 or 5 different functions at the same time.
Right.
You can see how they stack up,
Right.
the intercepts, the x-intercepts, all that good stuff.
Okay. That's DESMOS.
And
Dot
just
com
Google,
or-
yeah, it's .com, but if you really just Google search it, it'll take you straight.
Straight
It's the
there.
first search.
Okay.
So
Everybody got that? So,
that's the one I showed you, or one of them, yeah.
okay. So Desmos, okay? Go there. You can have, even if you don't have a graphing calculator, you can get there.
And they support mobile too. You can look it up on the phone. Or
Okay.
on computer.
Fantastic. Okay. Good. Appreciate that. I'll try to remember to put that on classes from now on, but I'll probably forget it. But it's here. Okay. All right. So use one and see. Graphic and see what happens. If you have something that's going up here or down there, no, that's not going to have a limit. But if you have something that is going somewhere and then at one point goes haywire, then you know it has a limit what it was going toward before it went haywire. Okay. Like sin x over x. Now, numerical investigations, basically what we just did, make tables of values of f of x when x is close to this value c that you're approaching. As x is getting closer and closer to c. See, if you do that with this one, you see it's always k. If you do it with this one, f of x equal to x, in other words, that's your, what they call the identity function, the positive diagonal line that you have here. Then as x gets close to any value here, f of x is getting close to that same value there. All the way out, they're going, so you're going close to, your function's getting close to the c. The y is going to c as x is going to c. Okay? Now, but you've got to do this for both positive, you're getting close to c from the positive side and from the negative side. You need two tables every time, unless you write them both on the same table, you could do that, and just and see what's happening. If this is going to -3 and that was going to +5, that's not going to exist, okay? So I can't think of anything that would, but that won't exist. If this is going to -infinity and this is going to +7, that's not going to exist, or vice versa. You have to have the same values coming from both ways. If both tables indicate convergence to the same number L, we take that as the estimate for the limit. Okay. Let's look at example 2, and I don't think they have example 2 either. Well, they might. Yeah, let's try it. Okay. Here's example 2. Investigate this. The limit as x approaches 9 of x minus 9 over the square root of x minus 3. Okay. It says investigate it graphically and numerically. All right. What's that? The square root of x. And it's just the square root of x, not the square root of x minus 3, but the square root of x in the square root minus 3. Well, this is graphically, okay? If you got a graphing calculator, you can do it and see what happens. Of course, when x equals 0, this will be minus 9 over minus 3, that would be a positive 3. So, yeah. And then when x is equal to, say, 1, you have, well, let's do 3. That would be 3 minus 9 would be a negative 6 over the square root of 3 minus 3. You'll have to do that on a calculator anyway, see what you get. And you can graph it, see what your graphing utility gives you, whether it's a calculator, Desmos, or something else. See what you get. This is what it's going to come out with. I don't know how your graphing utility is going to handle that, but you cannot put in a 3 here. I mean a 9 here, because that would give you 9 minus 9 is 0. Square root of 9 is 3 minus 3 is 0. So you have an indeterminate form there. Okay. So what you can do in a table, and this is numerically, is this. You can then let x approach 9. So I wouldn't start way here at 0. I would say start at 8 and at 10. And start 8 and do 8, 8 and a half, 8.75, 8 point, well, maybe 8, 8.9, 8.99, 8.999. See what happens. Then do 10, 9 and a half, 9.1, 9.01, 9.001, do that. See what you get there. And you'll see it's getting closer and closer to 6. That's a lot of work. Okay? Now, can I cheat and tell you how to do it analytically? This is graphically. The table is numerically. Let's see about analytically. When you look at that form right there, that function, what is the first thing that probably pops into your brain about what you don't like about it? Okay, a square root in that denominator. Do you remember how to get a square root out of a denominator? The conjugate, exactly. Let's try that and see if that helps make this make any more sense. Multiply this by what is the conjugate of square root of x minus 3? Square root of x plus 3. Okay, I'll buy that. But if you multiply the denominator by that, then you have to multiply the numerator by that same thing as well, which is the square root of x plus 3. Now, sure enough, folks, you just made your denominator simpler. What do you get? If you FOIL this, what do you get? X. Yeah, the innards and the outers go away because it's plus root 3 root x and minus 3 root x. Yeah, minus 9. You made your denominator nicer, but you really screwed up your numerator, didn't you? Well, let's do it. You did it, so let's do it. This would be, I don't know how you want to write it, x root x, okay, is the first. The outer is minus 3x. No, that's a plus. It's a plus. I can't read. Okay. Plus 3x minus 9 root x, okay, minus 27. Okay. Who thought of this anyway? Okay, this looks pretty bad. Okay. Now, okay. Now let's see. You still can't let x approach 9 because it's you still have a 0 in the denominator. And frankly, you'd still have it in the numerator. But let's see if there's any way to simplify that numerator any. Let's see. If I did x root x minus 9 root x, all right, let's back off. Okay. Sorry, we can use what we already had. Okay. That numerator, just the numerator. Okay. Let's group these two and group those two. That first group, I can factor out an x, right? And what do I have left? Square root of x plus 3. And in the second one, I can factor out how about a minus 9? And what do you have left? Square root of x minus, is it? Plus 3. Okay. And now I can do x minus 9 times the square root of x plus 3, right? Remember that? Factoring by grouping, factor out the square root of x plus 3. And now divide that by x minus 9. And what can we do? Oh, yeah. Okay, now let's take the limit of that. The limit as x approaches 9 of square root of x plus 3. What would that be? What's the square root of 9? 6. Look at that.
Okay. There we go.
Okay, so we did it graphically, or let them do it graphically. You could do it on Desmos or whatever, your graphing calculator. Or we could have set up our tables and let X get closer and closer to 9 from the left, 8.9, 8.99, 8.999, as many as you want, 9.1, frankly, I'd start there, 9.1, 9.01, 9.001, let it get there, and see, and sure enough, when you do that, you'll see that you get X is approaching 6, from the left and the right. Graphically, it looks like it is, but analytically, we showed it exactly. Okay. Now, sometimes analytically is not that easy to do, but you can always try it. Okay. Now, I shouldn't show you that yet. Sorry, I cheated you out of some of your tuition dollars coming up in the future, but it still works. Okay. This is graphically. This is if we did the same thing and numerically. Let me see if I can get hit the wrong button. Okay. No, this is a different problem. Sorry, they didn't show. They huh?
I could have sworn we just.
Well, wait. Let's see.
It's table 2. There we go.
Oh, I know. It skipped too much when I did this. Okay, sorry. Here we are. Okay. Here we did it analytically. I mean, numerically. They started from the left, I said from the right. And I said I would start at 8.9, 8.99, 8.999, 8.9999, and plug those in. That minus that is 0.1 here, divided by square root of 8.9 minus 3, and you'll get this, that, and see, closer you get to 9, this is getting closer and closer to 6. And if you kept going, adding more 9s here and stuff, you actually will get maybe on your calculator 5.99999, but at some point you'll start losing digits. You're going past the limit of your calculator, so don't do that. You see that's going to 6. Then on the right hand side, 9.1, 9.901, 9.001, you're getting closer to 9 there. And here you overshot it a little bit, 6.01, 6.001, and sure enough, take it on out, you're going to get closer and closer to 6. Take it too far, you'll start getting garbage digits out there. Don't take it that far. Stop when it starts backtracking on itself. You know you're beyond the limit of your calculator then. Okay? And sure enough, both of those are going to 6. Or, like I said, you could do it analytically, like I showed you, and you could show that also is going to 6. All right. Here is example 3. Investigate this one. The limit as x approaches 4 of x squared. Does anyone want to hazard a guess? 16. Okay, and you can do it graphically till the cows come home, and you see, sure enough, not only does it approach 16, it is 16. Okay, it approaches from the left, it approaches from the right. Sam, sit down, fight. You got it. Okay, you got the 16. Or you can do it in a table and let 4x approach 4 from the left hand side, 3.9, 3.99, 0.3, 0.9999, and on like this, and this is approaching 16, or 4.1, and 4.01, 0.001, 4.0001, not on number 4, but approaching it, and you're getting closer and closer to 16 here too. Okay? That's not really close, but these are getting closer, and you can see that if you keep on going for so far, you're going to get more and more precise. I'll almost guarantee you if you go too far out there, you're going to get beyond where your calculator can really calculate it right. You'll get garbage numbers out there, but you'll see it's going to 16. Okay, and there's no reason to do it analytically. Just plug it in. That's analytical. Okay. So, makes sense? Now, example 4. Oh, there's the, no, okay, this is example 4.
Just out of curiosity, we are in the 3rd edition, right?
Yeah.
Okay, I just saw the
Okay.
Pulaski calculus second, but that's
Okay.
just the PowerPoint.
Yeah. What they did when they went through the third edition, they didn't send the CD or DVD anymore.
Gotcha.
So I know I can somehow go online and get, that and show the proper, but the book rep for this company is almost impossible to get in touch with, and to get it set up is just more struggle than it's worth. Very little has changed. We'll run into some examples that have changed, and we'll talk about them. We'll do them in both, whichever. But this says second because I've got the CD for that, or I think it's a DVD. But I need to get the other, but I just haven't ever done it.
Hey, if it works, it works.
Yeah. As long as I don't have to. Okay.
There we go. Yeah.
You got it now. All right. Now, they want us to verify numerically that the limit as h approaches 0, okay, I'm looking at the wrong problem, as h approaches 0 of e to the h minus 1 over h is equal to 1. We want to verify numerically that that is true. Okay. Now, again, here's the problem. If you try to plug it in, which is the first thing I'll do, what is e to the 0? 1. 1 minus 1 is 0 over 0 in determinate form. So we don't know if there's a limit or not. This is telling us that limit is 1. Okay? So it says do it numerically, and we could, and it's just like we've done before. I would say, and like they say, we'll set up 2 tables. Here we'll put our h, and here we'll put our e to the h minus 1 over h. Okay? And we'll start with, since we're having h go to 0, I would say start from negative 0.1, negative 0.11, negative 0.11, I'm sorry, 0, 1, 0, 0, 1, and go as many as you want, and then do the same thing for, and I'm going to be lazy and only write one table, 0.1, 0.01, 0.001, and go to town with those, and take them as far as you'd like, and see what that limit will be. And they actually started with 0.02. I'm sorry, I started with 0.1, but I got down to the third step as fast as they did, so. What's that?
I said parentheses will change everything.
Right.
I was trying to grip it weird. So for negative 0.1, I got 0.95.
0.95 sounds reasonable.
I don't know how many decimals are.
That's fine.
Okay. Let's see. You said negative 0.01. I got 0.99.
What next?
5.
5, okay. And 0.9995. Right. They did one more, negative 0.0001. Yeah, okay. And if you did on the plus side, 0.1, Okay. Okay. Yeah. Okay. So you see, this is getting closer and closer to 1. That's getting closer and closer to 1. Coming from the lower side, you're approaching 1 from the lower side. Coming from the positive side, you're approaching 1 from the upper side. So, yeah, as you approach 0. So you could do it graphically if you wanted to. You've done it numerically. That's what they ask us to do. I'm not sure. I haven't tried lately to see if there's an easy way to do it analytically here. I'm guessing not, but I can't say that for sure until I try it. So, but this was easy enough to do. Okay, that's all they ask. Verify numerically. Okay. Let's look at example.
Just to let you know, it's basically the same thing, but on the book it's 2 instead of E.
Yeah, they started at .02 and point.
No, I'm not talking about.
Oh.
I'm talking about our problem is different. We have the limit of h as h approaches 0 to h, 2 to the h minus 1 over h. That's what I have.
Okay.
I don't know if that's.
Example 4.
That's what I have.
Wow, mine is exactly this one, and I'm in the same edition.
Yeah.
E to the H
Third
minus
edition,
1.
right?
Third edition.
I don't know.
I think it's a different printing.
Maybe.
This is bizarre. Okay.
But anyway, I mean, same concept.
Okay. I can't adjust for that.
I
Okay.
actually like it
Yeah.
better with E. That way
Yeah.
you get a little practice with that.
Yeah. But it's just another power function. I mean, exponential function. You're 2 to the x, 2 to the h, right?
2 to the h, yeah.
Yeah. And ours is e to the h, right?
Exactly.
Okay. Wow.
Yeah,
Strange.
Kind of strange, yeah. I actually prefer it the other way, but.
Okay. All right. Let's move to example 5. Oh, here's the table that y'all just did, except that they started at .02 and .005. I started at .1, negative .1 and .001. So I don't know why they had a big jump there and then smaller. But it doesn't matter. It doesn't matter where you start, really, and go. Okay. Or at least I say that. But that was graphically. This is numerically. I'll blow this up. Whoops. I'll blow this up so it's hard to read when you're home or something. There is what we did. And I don't know why this is the same as example 4 in your book, which is the same edition. That's bizarre. Okay. So let's move to example 5. Okay. This is a weird one. What we have here is the limit. Investigate the limit as x approaches 0 of sine of pi over x. Okay? It says do it graphically and numerically. Okay. I say don't bother. Okay? And here's why. My rule of thumb, always plug it in first. See what happens. What happens if you plug in x approaches 0? What does this give you? Undefined. Not as indeterminate. Undefined. Pi over x is going to infinity. As x approaches 0, from the positive side, as x is approaching 0 here, this is pi over 0, that's going to infinity. I mean, just skyrocketing to infinity. As it approaches 0 from the left-hand side, it's pi divided by a slightly negative number. That's approaching negative infinity. Okay, guess what, team? There's no limit to this thing it keeps getting bigger and bigger and bigger. The sign of whatever it is there is staying between plus or minus 1. That's what sine does. It goes up and down and up and down and up and down, up and down, plus or minus 1. From the negative side, it does the same thing. So guess what? This is what the graphic looks like. Look at that and say, there is no limit.
Isn't it squished because it's
Yeah, because as x gets closer and closer to 0,
right.
you're getting a bigger and bigger number, and you're putting all those into signs, and it's going up and down and up and down. So you're way, way around there somewhere, or on the negative side doing that. It's ridiculous because that limit doesn't exist. And if that limit doesn't exist, how can you take the sign of something that doesn't exist? Yeah. But if you were to try it numerically on the table,
That's not too bad.
you don't get anything that looks as bad, but
That's strange.
where did they pick these numbers from? If we had done what we did before, okay, if we had done 0.1, 0.01, 0.001, 0.0001, and 0.0001, put those in there, you would have gotten, let's just do negative 0.1. That would have been a minus 10 pi. What's the sign of minus 10 pi?
Zero.
0.
Yeah, right.
Okay? And if you'd done 0.01, that would have been minus 100 pi.
Same thing.
Still 0.
Oh,
And
wow.
0.001, 0. You would have said, oh, the limit is 0.
Right.
But what you were just doing, you were just picking just these things that get closer and closer here and here, but you just picked the ones that were at 0. You left off the ones in between, and that's why on this one, they chose numbers other than 1. So this would be I'm still not convinced that's right. Just someone,
Can we plug it in?
yeah, plug in pi over 0.03, negative 0.03. I'm sure they must have done it right, but I'm trying to do it in my head.
Sign
Pi divided by, well, just don't even do the sign yet.
Yeah,
Just do pi divided by, oh, that probably won't tell you much.
pi divided by what?
By negative 0.03.
Yeah. Negative 104.72.
Okay, and then take the sign of that.
We got 0.866.
Yeah. So they did it right.
Okay.
But if you had done the same pattern we did before, you would not gotten that. You would have gotten 10 pi, 100 pi, and those would have all been 0. You would have thought they were all zeros. They're not. So then you would have to just know to pick something else here, and I'm not sure I would have known to do that.
Yeah.
So why even mess with that? Just look at that. Undefined. You can't take a function of an undefined number because what are you taking it off? And sure enough, this shows it has no limit. It just is scattered always between -1 and 1, which is, of course, what your graph shows. And it's just more and more, they get more and more compressed the closer you get to 0. And this doesn't have a limit here, so it certainly doesn't have a limit here either.
Now, almost, I mean, instead of it really having like a limit of one number, it's like a gap just
Yeah.
between both sides.
Yeah.
From point 1 to,
Yeah.
the other negative point.
Yeah. Because the closer and closer you get to 0 from either side, the faster and faster you're going up and down and up and down and up and down.
Right.
So yeah, and you never, it can't, because going there and this one's going here. And
Right.
how could there's no limit between those two numbers, so how could your answer have a limit? It can't. So I say plugging it in made the most sense. As soon as you see not an indeterminate form, but an undefined form, no limit. Just stop right there. There is no limit. All right. Now, and this is the table. We already looked at that. All right. Now, what we're going to do now is the limits that we've discussed so far, when there was one, they were two-sided limits. The function had a limit coming from the left and from the right, and they always tended to meet at the same place. This one, however, does not. Okay? This is a legitimate function here, the graph of x over absolute value of x. And sure enough, if you just have the limit as x is approaching anything other than 0, this is going to have a limit. -1 down here, +1 up there. Okay? But when you have x approaching 0, this is an indeterminate form. Now, just because it's indeterminate doesn't mean it's going to have a limit. Okay? It just means it's indeterminate. The others we've hit so far indeterminate did wind up with limits. But let's see what happens. If you let x get close to 0 from the positive side, from the negative side, then this is a negative number, right? Absolute value of, say, -0.1. This will be the absolute value of -0.1, which would be 0.1. So this will be -0.1 over 0.1. It's going to be -1. Yeah. And as you get closer, that would be 0.01 divided by a -0.01 divided by 0.01. That's still going to be -1. So coming in here, as you're approaching 0, that's approaching -1. It's always -1 out here. -2 over 2 is -1. -3 over 3, -1. All those are, and it's going to be -1 all the way in until, but you can't define it at x equals 0. But if you use positive 0.1 over 0.1, that's going to be a positive 1. All these are positive ones here until you get to 0. You can't do that one because these come into different limits. This limit does not exist. Okay? Question? Yeah.
Do we need to know, it's just something we have to know the continuity part?
The what?
Are we going to need to know continuity?
Yeah, we're going to talk about continuity later. And this limit does not exist at x equals 0 because the two limits they both exist at x equals 0, but there are different values at x equals 0. So this is not a continuous limit. You're absolutely right there. Now, I don't know if this is helpful or not. Whoa. Oh, I have to get out of that. Okay. But remember what we did before? We did, here is your f of x, the numerator, let's call it g of x equal x, and let's go to a different color, dark green it was, wasn't it? Okay, let's go with dark green. H of x is equal to absolute value of x. So I drew in g of x already. That's the identity function. But if I draw in the h of x here in green, the absolute value function is this one. Okay? So on this side, the ratio of this to that, these are the same values, but exactly opposite each other. So this ratio is -1, that ratio is 1. So that shows this, it can't have a limit at x equals 0. This is going to -1 here, that's going to +1 there. No way that it's ever going to make discontinuous limits. You got it right on the nose there.
put a negative or outside of the absolute value, would that flip it?
Okay.
Is that correct?
Yeah, okay. You take it you're meaning this. Let me go back to dark. Okay. Let's do k of x equal minus absolute value of x.
Yeah.
Okay.
So
If you have that.
would that give you the inverse of
Yeah.
that? Okay.
Yeah, because you're negative in both cases. I probably should have done a different color. What color you want this one?
Well, how about that light blue?
Light blue right there.
You can't really get into the red.
We can, yeah, okay. Then this one would be, so let's do this one light blue. What would that be? 0 would be 0. 1 would be minus 1. Minus 1 would be minus 1. So sure enough, that's that one.
Okay.
Yeah.
Yeah.
I think that's what you were saying.
Exactly. Yeah. Instead of going like this, just
Yeah.
flip it upside down. Yeah.
Got it. Yeah. And if you had something like that, then it would have been, depending on what you put over it, if it was x over, or I have a minus in front of this, that would have been a plus 1 on this side and a minus 1 on that side. Okay. All right. All right, there's, whoa. Okay. They have a little blurb here that they didn't do, so let me, should have done it probably before I started this. Let's clear all the ink and let me write this first. Let me go back to black or dark. Okay. The limit exists if both of the one-sided limits being x approaching the whatever that c is from the left and x approaching from the right. If both of those are true, if both one-sided limits exist and are equal. Okay, pretty ugly writing. Okay, so the limit will exist. Both of these things have to be true. The limit, whatever limit you're dealing with, if x approaches c from the left and x approaches c from the right, they both have to have limits. Both one-sided limits exist, but not only do they exist, they must be equal to the same value. And again, it may not have a value at x equals c, but they both must exist. So if you have something that has no limit from one side and a limit from the other, then that limit doesn't exist. If it has a limit from one side and a limit from the other side, but they're not the same, the limit doesn't exist. But if it has a limit from this side and a limit from that side and they are the same, then the limit itself exists. That's what they're getting at here. Okay. Here are some figures. We don't have functions for them. Thank you very much. But this is example 7. The figure f in the function f in figure 9, this says figure 7 here, but figure 9 in your text, is not defined at x equals c. The limit itself is not equal at x equals 0, at x equals 2, or at x equals 4. The function f of x equal to, and it's a piecewise defined function. This value over here, this value there, this value there, okay? And this goes on indefinitely here, goes on indefinitely there, okay? Well, the limit from the left as x equals 0 obviously doesn't exist. That's like that sign with pi over x. It just doesn't exist. The limit from the right does exist, but the limit at x equals 0 can't exist because it doesn't exist here, and even if it did exist, it wouldn't exist at the same value here. So that loses on both counts, okay? Now, x equals 2, the limit from here exists, and the limit from there exists. So that part works. The limit from both sides exists. but they're not equal to each other, so the limit at x equal 2 doesn't exist either. That has one value, 3, another value of 1. Those are not the same. But at x equal 4, even though the function doesn't exist there is no value for x equal 4. The limit as x approaches 4 from the left and from the right has the same value. I don't know what it is, 1.5 or whatever that is. It is the same value, so that limit does exist. Okay? These have limits from both sides, but they're not the same limits. This one has limits from both sides, and they are the same. This one only has a limit from the left, no limit from the only has a limit from the right, no limit from the left, so it can't exist at all. Even if this came in somewhere here, that still couldn't work because this limit doesn't exist and that limit does exist. So that would still be the limit at x equals 0 can exist because it doesn't exist from the left anyway. Okay. Now, I probably should have blown this up, sorry. I don't know if it does any good to blow it up now, but this is what we were talking about. Sorry, I forgot to. Okay. Now, here's some other examples. Okay, I can't blow up the whole thing, but I can blow up part of it. Okay. In the first figure here, alpha of x equals 1 over x minus 2. That is undefined where? First function there. Undefined where? Where is this function not defined? X equal 2. It's not defined there. What is the limit as x approaches 2? Plug it in. 1 over 0. You can never do 1 over 0, so this limit's not going to exist. Well, let's look at it graphically. It's going to negative infinity here, positive infinity there. The two will never equal the same. Number one, they don't exist from either side, and what's more, even where they're going doesn't exist. Okay, so that's obvious. Now, limit of that is x is approaching 1 or 7 or 14 or negative 35 halves or whatever. Those limits all do exist. You know, anything in there, just x equal 2, it doesn't exist at all. Now the second one, alpha of x equals 1 over x squared. Now you might say, well, from the left it's going to positive infinity, from the right it's going to positive infinity. So do those ever meet? No, they don't. Okay, because they're just getting bigger and bigger and bigger, but they don't have the limit up there at all. Okay. Well, how can you tell that? Well, plug it in, plug it in. As x is approaching 0, this is 1 over 0, undefined. You know that's never going to work, ever. So don't even try. Don't waste your time doing it. You know that's not going to exist. And sure enough, graphically it doesn't exist, and you'll never find the limit. Okay? Plug in any value, 0.1, 0.01, 0.0, negative and positive, you'll see there is no limit. They're approaching. They just keep getting bigger. Okay. Then this third one. Okay. Oh, no, I'm sorry. Oh, this is C. This is example 8C. And by the way, let's go back. Notice here they kept putting in asymptotes. When alpha of x approaches either positive infinity or negative infinity, as x approaches C from one side or both sides, the line x equals C is called a vertical asymptote. If that's the case, the limit doesn't exist. Okay? Now, here's one. Alpha of x is equal to log x. Okay? Now that's natural log of x. That would have been any log of x, any base, whatever you put there. this is always going to be the case. That is never defined when x is negative. Ever. Nor is it defined when x is 0. Ever. Okay? It's approaching negative infinity as x gets close to 0. So that is a vertical asymptote, but there's no values at all over here on the negative side. On the positive side, it doesn't have a limit as x goes to infinity. It keeps climbing, never is leveling off. It's just climbing at a slower and slower rate, but it still has no limit, okay? Vertically. But any value you pick, 0.7, 0.03, 2.7, those limits all exist, whatever the value of log x is at that point. You just can't put in a negative, you can't put in 0. You could have put in any positive value you want, small positive value, large positive value. That function will exist anywhere except 0 and is not even defined for 0 or less than 0.
Is the horizontal asymptote at 4?
No, there is no horizontal asymptote. That's what I'm saying.
Okay.
It keeps climbing indefinitely.
Okay,
It
gotcha.
climbs at a slower and slower rate, but it keeps climbing.
Gotcha.
It never
So,
levels off.
Gotcha.
It just goes up more slowly, but it never. You can put in any large number you want, and then put in a much larger number. It's still going up and never ceases to go up. So it doesn't have a horizontal asymptote either. That's what I'm trying to say. There's a better word. It has a vertical asymptote on this end, no asymptote on that end. Yeah.
that's awesome.
All right, and I believe there is a conceptual insight here. You should not think of an infinite limit as a true limit. We can write it down that it's going to infinity, but really it's not. Okay, now let's just back up just a little bit. Remember this one? This is not going to infinity, but it has no limit. And so you can't say its limit is infinity. It isn't. The limit of that part is infinity, which isn't a limit. But then when you take the sign of that, it just stays between plus and minus 1. So you can't say that even has an infinite limit. The sign function doesn't. It has no limit. And these have no limits, but they get used to writing the limit as positive infinity, negative infinity, positive, negative. But still, that's not a limit. It really isn't. So don't think of that as a number, the symbol. It's just a symbol. All right, that ended the slideshow, and I'm afraid we ended our time too. Do y'all feel like the preliminary questions are worthwhile or not? Okay. Do you think we need to do them in class, or would that be something you'd like to do at home with your homework exercises? Knowing that all those answers are in the back, but if you like that concept of doing it in class, we'll start with that next time. Start with that? Okay. So we'll start with the preliminary questions on 2.2 next time. And let me get something in here to mark it. There it is. But then on the slides, we'll start with 2.3. Okay? And let me go and give you your homework exercises for 2.2. You can do either 1 or 3 or both. Do number 5. Do number 7. This is page 70 and following. Then any of the odds 9 through 15. Any of the odds 17 through 37. Try number 39. It's a different function, but I think you've run into it before. That's 39. Then do any of the odds 41 to 47. Try 49. Either 51 or 53 or both. Do 55, or at least, I think that's pretty easy to do. And then do any of the odds 57 to 61. And then look at 63 and or 65. You can do them or not. Now, I don't ever assign the further insights and challenges. However, I take a look at those, and number 66 is referring to the Fraunhofer diffraction pattern. So since somebody's name is there, you could do a paper on Fraunhofer if you wanted to. Or how did he come up with this diffraction pattern, or what difference does it make, how is it used? You could do that. That's really a lot more of a physics exercise than math, but since it's in the book, you can do something with it if you'd like. But the rest of them is just only if you want to look at them. That's all. And starting next time, we're going to go over the basic limit laws, which I've already introduced to you, at least the beginning of them. And we'll do a few more beyond that. So we'll pick up. Once we do the preliminary questions for 2.2, we'll move right into 2.3. Good deal.
Just reminding you, about this Wednesday.
Yeah.
Here, but
Oh, and let me tell you, I wish I had said it before Rodney left. I do have a small adjustment to my schedule, probably 2 days this week. I have a doctor's appointment on tomorrow morning. I'm going to miss my trig class. And I probably won't be back for office hours between 10:45 and 12:30. Or if I do get back, it'll be really close to 12:30. Maybe after 12:30, but that class knows not to leave. I will be back sometime. But that also affects Thursday because I'm going to try to make up my trig class from 10:45 until 12. And that means my office hours will only be 12 to 12:30 on that day, not 10:45 to 12:30. So both of the next 2 days, I probably won't have any office hours tomorrow because I'll be coming back from the doctor's, and I will only have 30 minutes of office hours on Thursday rather than an hour and 45 or whatever I usually do. Okay. All right, good deal.
everything.
Yeah, it's just in between every 2 treatments, I have to see the hematologist. And hopefully the counts are going down because I had a treatment. So hoping that.
All right, listen, you take it easy, and y'all have a good class. I'm sorry I'm going to be away, but
Right.
I'll see you this next Monday.
Yeah, okay. You only want math once a week. I can get the idea. Yeah, okay. All right, take care. Enjoy your trip. Okay. I wasn't sure if you were in the class or not. Yeah, but because they took out all the unpaids, I don't know if they got you back in or not. Do they? Okay. All right. Good deal.